Classical bits leverage the NOT gate to undergo a bit flip. The following truth table shows us that a 0 becomes 1 and a 1 becomes 0 after applying the gate. Is there a quantum analog for this gate? In quantum computing, quantum bits or qubits are represented in the form of vectors, and any arbitrary gate is represented in the form of a matrix. Some of the gates used in quantum computing are the Y gate, the X gate, and the Z gate. These are collectively called the Pauli operators. Each has its own matrix representation. The Y gate, for instance, contains imaginary elements. The Z gate contains a negative element. The X gate contains zeros and ones. We are going to look at the X gate in more detail. This gate is similar to the NOT gate we encountered earlier. Hence, it flips a ground state or 0 qubit to its excited state, that is 1, and the other way around. This is how we can prove its operation mathematically. It is essentially a matrix vector multiplication. We can understand the operation visually as well. Traditionally, this is done using a block sphere, but we are going to see the result of its matrix applied to the Cartesian plane. Consider two unit vectors, the red one for the excited state and the green one for the ground state. Then applying the matrix will result in the following transformations. The 0 state comes in the ones position and vice versa. Again, this is not a true representation, but it is helpful to think of it this way. Now let's talk about superposition. It is represented by the state psi. Alpha and beta represent probabilities of measuring the states 0 and 1 respectively and must sum to 1. Here alpha and beta need to be squared as they are written under a root, as in the following examples. What can help us achieve superpositions? The Hadamard gate. Applying it to the 0 state gives us an equal superposition between 0 and 1. Applying it to the 1 state gives us the same result but with an opposite sign. This is what its probability distribution graph looks like in an ideal case. What happens when we apply an X gate to a superposition state? It simply operates on the states individually and flips them. The same applies if we started with the 1 state. Superposition states provide a tremendous speed up in quantum computing. If one qubit has 2 superposition states, just 8 qubits can have 256 superposition states in accordance with this formula, where n is the number of qubits. This is just one of the 3 properties quantum computers use to get an advantage over classical computing.